1 year ago, the sixth largest earthquake ever recorded tore through 500 kilometers of fault off the coast of Kamchatka. Partway through, it stopped. The stretch of plate boundary it left untouched has been sitting locked and loaded ever since. This week, both ends of that unbroken stretch lit up with earthquakes within about a D, high and a half of each other, right as the rest of the planet went unusually quiet seismically. By the end of this, you'll understand what these smaller earthquakes are actually telling scientists, what the last full rupture in this exact spot did to an entire town, and precisely what to watch for next. The Kuril-Kamchatka arc produced 10 cataloged earthquakes across a roughly 36-hour window this week, and every single one of them landed on the same stretch of plate boundary in the Northwest Pacific, a boundary that runs over 2,000 kilometers long. The magnitudes range from 4.5 to 4.9. 4 of them hit magnitude 4.9, one east of the Kuril Islands at a depth of just under 10 kilometers, one roughly 200 kilometers southeast of the Russian town of Severokurilsk, one 85 kilometers south of that same town at a depth of nearly 58 kilometers, and one in the Kurils at 76 kilometers down. 2 magnitude 4.7s followed, one south of Shikotan Island and one in the southern Kurils. 3 more events at 4.5 and 4.6 rounded out the picture, including 2 on the Japan Trench off the Tohoku coast, the southern continuation of this exact same plate boundary. None of these earthquakes is newsworthy on its own. A magnitude 4.9 on a remote oceanic arc breaks nothing and hurts no one. The Kuril arc produces moderate earthquakes constantly because this is one of the most seismically active boundaries anywhere on the planet. That boundary deserves 30 seconds of context before going further because its statistics are extreme even by Pacific standards. The Kuril-Kamchatka Trench marks the line where the Pacific Plate dives beneath the Okhotsk microplate, and the trench floor drops to more than 10,000 meters below sea level, among the deepest points on Earth. The convergence rate runs somewhere around 75 to 80 millimeters a year, among the fastest of any major subduction zone anywhere in the world. That same engine feeds one of the densest concentrations of active volcanoes on the planet, sitting along the arc above it. In the instrumental era, this single boundary has produced at least 3 earthquakes of magnitude 8.5 or greater in 1952, 1963, and 2025, with a magnitude 8.3 in 2006, not far behind. Almost no other subduction zone anywhere can match that record. If earthquakes were scattering randomly along this arc, you wouldn't expect them to sort themselves into 2 tight clusters with an empty gap in between. Random processes do tend to clump, but this isn't ordinary clumping, because the location of that quiet middle section isn't just any random stretch of fault. It's the one sectio N of this entire boundary that seismologists have been watching more closely than anywhere else on the arc. To understand why, you need to go back almost exactly 1 year, and that's where this stops being a story about magnitude 4 earthquakes. There's one more piece of context that sharpens the picture, and it comes from looking at the planet as a whole. Over the past week, global earthquake activity actually dropped noticeably. The worldwide count of magnitude 4.5 plus earthquakes over a 7-day window fell by roughly 16% compared to the prior R week. The largest earthquake recorded anywhere on Earth during this stretch was a magnitude 5.2 in central Peru, an event roughly 130 kilometers down inside a subducting slab, completely unrelated to anything happening in the Northwest Pacific. Nothing at magnitude 6 or above occurred anywhere on the planet for days. One environmental explanation can be ruled out immediately, since this kind of claim tends to surface whenever a cluster like this appears. The sun had nothing to do with it. This burst of activity coincided with one of the quietest stretches of space weather all year. Geomagnetic activity sat near the floor of the scale. Solar wind speed stayed slow and steady. Background X-ray levels sat at baseline. Whatever organized this pattern of earthquakes, it was working from underground, not from space. So this burst isn't part of some broader global uptick in seismic activity. If anything, the planet went unusually quiet this week. Against that quiet backdrop, a single arc lighting up with 7+ earthquakes above magnitude 4.5 in a day and a half stands out the way a single lit window stands out on an otherwise dark street. Whatever is happening along the Kuril-Kamchatka boundary right now is local. The energy is concentrated there and effectively nowhere else on Earth. That's the setup. Now here's why the geography of these 2 clusters matters more than anything else in the story. On July 29th, 2025, a little over a year before this week's burst, the Kamchatka end of the same plate boundary ruptured in a moment magnitude 8.8 megathrust earthquake. It tied for the 6th largest earthquake ever in Stas, mentally recorded anywhere in the history of seismology. The numbers from that event are genuinely difficult to take in. The rupture tore along the plate interface for somewhere between roughly 390 and 600 kilometers, depending on which model you use, across a fault surface up to 200 kilometers wide. In localized patches, the two sides of the fault slipped past each other by as much as 30 to 40 meters. The rupture itself lasted somewhere between about 190 and 270 seconds, meaning the fault kept tearing for close to 4.5 minutes straight. Analysis of the rupture, backed up by hydroacoustic recordings, shows it propagated predominantly southwestward from the epicenter, extending roughly 500 kilometers down the arc toward the Kurils. The tsunami that followed was severe along at least 550 kilometers of the southeastern Kamchatka coast and into the northern Kurils. Survey teams recorded run-up heights of at least 2 to 3 meters in most places, and more typically 5 to 10 meters along a 100-kilometer stretch of Kamchatka coastline. The water reached 10 to 16 meters. In the northern Kuril Islands, it reached over 30 meters in places, roughly the height of a 10-story building. Smaller waves crossed the entire Pacific basin, reaching Japan, Hawaii, and the Americas, and tsunami alerts went out across the whole ocean. Remarkably, casualties from the event itself were minimal, largely due to sparse population along the ruptured coastline, effective evacuation procedures, and favorable rupture geometry. The aftershock sequence behaved exactly the way great earthquake sequences are supposed to. The United States Geological Survey issued a formal aftershock forecast, and the sequence largely followed it, including strong aftershocks in the magnitude 6 to 7 range within days and weeks of the main shock, among more than a few thousand aftershocks logged in total. Through the year that followed, the sea decayed steadily the way these things normally do. By this summer, the arc had settled into what looked like a fairly normal post-megaquake rhythm, gradually fewer events, gradually smaller ones, the system slowly working through the largest stress change it had experienced in roughly 70 years. Here's the detail that matters for this week. The rupture propagated southwest down the arc, and then it stopped. It never broke the full length of the boundary. The section of the interface, south of where it quit, running through the central and southern Kurils, has not ruptured. All the strain that section has been building up over decades remains locked in place, fully intact. Seismologists have a specific term for a stretch of fault like this. They call it a gap. A seismic gap isn't an empty space in any meaningful sense. It's a loaded one. The Pacific plate dives beneath this arc at somewhere around 75 to 80 millimeters a year, one of the fastest sustained convergence rates of any subduction zone on Earth. Where the interface is fully locked, that motion stores roughly a meter of unreleased slip every 12 to 13 years. The section south of the 2025 rupture has been accumulating strain this way for decades at minimum, and it didn't let go last year. There's a second effect layered on top of that steady accumulation, and it's the textbook consequence of every great earthquake. When a magnitude 8.8 releases centuries worth of accumulated strain along 500 kilometers of fault, the surrounding system doesn't simply relax back to normal. It reorganizes. The stress at the ruptured section sheet doesn't just disappear. A portion of it transfers along the boundary, concentrating specifically at the margins of the rupture, beyond both ends of where it broke. Seismologists call this mechanism Coulomb stress transfer, and its standard signature is elevated earthquake activity at the edges of a rupture zone for years afterward. One more point about timing is worth mentioning here, because it's the kind of detail that's either meaningless or meaningful with nothing in between. This burst arrived almost exactly 1 year after the megaquake, roughly 370 days later. Nobody serious in this field believes earthquakes follow a calendar or keep anniversaries. Coincide. Hence is coincidence until proven otherwise. But the 1-year mark happens to sit roughly on the timescale over which post-seismic processes, afterslip on the fault, slow relaxation in the mantle beneath it, continue redistributing stress along a boundary following a great rupture. A year out is not late in geological terms for a magnitude 8.8 system to still be actively reorganizing. In that sense, the timing doesn't prove anything on its own, but it fits. Now look at this week's map again with all of that in mind. The northern cluster sits at and just beyond the southern end of the 2025 rupture zone, exactly where transferred stress would be expected to concentrate. The southern cluster sits at the far end of the unruptured section, right where the Kuril arc hands off to the Japan Trench. The two ends of this loaded gap produced or earthquakes within the same 36-hour window, while the gap itself stayed silent, and while the rest of the planet stayed unusually quiet too. The fault system appears to be sketching an outline, and the shape it's sketching happens to be the one section of itself that hasn't yet failed. The historical record for this exact arc suggests that outline deserves to be taken seriously. Subduction zones sometimes fail in sequence, almost like a zipper. One segment ruptures in a great earthquake, and months or years later, the segment right next to it follows. The most famous example is Sumatra. In December 2004, the magnitude 9.1 Sumatra Andaman earthquake ruptured and triggered the Indian Ocean tsunami. 3 months later, in March 2005, the very next segment to the south failed in a magnitude 8.6 earthquake. Same boundary, adjacent segment 90 days apart. You don't even have to leave the Kural arc to find the same pattern playing out. In November 2006, the central Kurils, the exact section that sits between this week's two clusters, produced a magnitude 8.3 thrust earthquake on the plate interface. 59 days later, in January 207, a magnitude 8.1 struck in nearly the same location, on a structure just seaward of the trench that had been loaded by the first event. One great earthquake effectively manufactured a second great earthquake in under 2 months on the same arc, in the exact middle section relevant to this week's story. That 2006 and 2007 pair is worth a closer look because the mechanism behind it is instructive. The first event was an interplate thrust, the classic megathrust type, where two plates lurch past each other along their shared contact surface. The second was something different, an outer-rise normal faulting event, a rupture inside the Pacific plate itself, seaward of the TR, where the plate bends before diving downward. The first earthquake changed the stress on that bending region, enough to break it on its own. That's the core point here. A great rupture doesn't just relieve stress in one place, it moves stress elsewhere. And the places it moves, that stress to, can fail on their own separate timeline. 59 days was the schedule that particular time. That precedent is exactly why the question being asked this week isn't paranoid speculation. It's the same question this arc has already answered once in the affirmative within recorded history. When a 500-kilometer rupture stops partway down a plate boundary, the section B, Ural candidate for the next large event. Whether that takes days, years, or decades is the part nobody can answer with any confidence. But this particular arc has demonstrated it can happen in a matter of weeks. And what the last full-scale rupture of this exact neighborhood did 74 years ago is the reason the stakes here aren't abstract. The reference town that keeps appearing in this week's earthquake catalog is Severo-Kurilsk on Paramushir Island at the northern end of the chain. The listings literally measure the new earthquakes by their distance from it. 85 kilometers south of Severo-Kurilsk, 204 kilometers southeast of Severo-Kurilsk. There's a grim irony in that, because Severo-Kurilsk is the site of the deadliest tsunami in Russian history, produced by this exact same stretch of plate boundary. On November 5th, 1952, in the early morning hours local time, the southern Kamchatka and northern Kuril section of this interface ruptured in an earthquake, estimated between magnitude 8.8 and 9.0, still the most powerful earthquake ever recorded in Russia, a record the 2025 event only tied, not surpassed. The shaking itself killed relatively few people. Residents of Severo-Kurilsk did exactly what coastal communities are taught to do. They fled to higher ground, and they survived the first tsunami wave. Then, many of them came back down to check on their homes, to search for belongings, to look for family members. And the second wave, the largest of three, estimated at roughly 15 to 18 meters, caught them in the streets and effectively erased the town. The details of that morning have been pieced together from survivor accounts collected decades later. The first wave arrived roughly 45 minutes after the shaking, and it was survivable since most of the population was already up on higher ground by then. The gap after it was the trap. Tsunamis typically arrive as a series of waves, often separated by tens of minutes, and later waves are frequently larger than the first. The people walking back down into Severo-Kurilsk had no way of knowing that, because nothing in their prior experience or their government's public guidance had told them so. The second wave came in at roughly 15 to 18 meters and moved through the town at the speed of a fast-moving car. A third wave followed after that. By sunrise, the town functionally no longer existed. The official Soviet death toll listed was in the low thousands. Modern estimates run considerably higher, commonly into the several thousands, and by some estimates, into the tens of thousands. Part of the reason for that lasting uncertainty is itself part of the story. The Soviet government classified the entire disaster. There were no newspaper reports, no published casualty lists, no public record of any kind for decades. Hades. A town was destroyed. A huge number of people died. And officially, none of it had happened. The true toll may never be fully known. Severo-Kurilsk was eventually rebuilt, partly on higher ground. 74 years later, the instruments recording this week's burst of small earthquakes are measuring their positions by distance from that same rebuilt town. That's what the full-scale version of this stretch of boundary failing actually looks like in the historical record. It isn't a hypothetical scenario. It happened within living memory. The quiet gap sitting between this week's two clusters is right next door to where it happened. The earthquakes in this week's burst weren't all the same type of event, and those differences carry real information. Depths range from just under 10 kilometers to 76 kilometers. The shallowest events sit right at the level of the plate interface itself, the locked contact surface where megathrust earthquakes are born. The events at 50 to 76 kilometers are something different. Intraslab earthquakes, breaking inside the descending Pacific plate as it bends and sinks, redistributing stress within the slab itself rather than along the boundary between the two plates. Both populations of earthquake showed up in the same window, and that ambiguity cuts both ways. If follow-up analysis confirms to shallow events as thrust-type ruptures on the interface, it strengthens the reading that the locked, loaded section is being pushed toward the top of its stress cycle. If most of the burst turns out to be adjustment happening inside the sinking slab instead, it says more about the plate flexing at depth than about the megathrust zone itself. A useful way to picture the difference is to think of the subduction zone as a conveyor belt paired with a clutch. The interface, the contact surface between the two plates, is the clutch, and when it's locked, the whole system stores up energy. The slab sinking below is the conveyor itself, and it flexes and cracks internally as it descends, whether the clutch is locked or not. Intraslab earthquakes are the conveyor creaking. Interface earthquakes are the clutch slipping. Only the clutch slipping can produce something on the scale of a magnitude 9 in a Pacific crossing tsunami, which is exactly why the question of which population dominated this week's burst isn't academic. As of this week, the reviewed focal mechanisms for these events hadn't yet been published, though they typically appear within days. They're the single most important near-term piece of evidence in the story. A specific, checkable observation arriving on a known schedule that will meaningfully shift the interpretation one way or the other. The honest statistics need to be stated plainly here, because they're the guardrail on everything else in this story. Roughly 19 out of 20 moderate earthquake clusters like this one are followed by nothing larger. The baseline probability that any given cluster turns out to be a foreshock sequence for something bigger within the following G-days runs somewhere around 5 to 6%. Foreshocks are only ever identified in hindsight. No instrument on Earth can reliably tag one in advance. By far, the most likely outcome of this week's burst is that it simply fades back into the ark's ordinary background chatter. But the same honesty requires the other half of that sentence, too. That identical statement would have been true of the moderate earthquakes that preceded nearly every great earthquake in recorded history, right up until the moment the main megaquake actually arrived. The statistics bound the odds. They don't dismiss the geography. And it's the geography here, the bracketing of a known loaded gap, 1 year almost to the day after the rupture that created it, that keeps this burst from reading as ordinary background noise. One claim circulating this week deserves a quick, direct answer. The idea that agencies are somehow hiding earthquakes because seismograph stations visibly record more small events than what shows up in the public catalogs. The real explanation is reporting thresholds, not conceal, meant. Remote oceanic arcs like the Kurils have a practical reporting floor sitting around magnitude 4 to 4.5, and automated detections below review thresholds simply aren't published until analysts confirm them manually. Different agencies apply different cutoffs, which is exactly why one data feed might show 3 events where another shows only 1. And this arc actually supplies the clearest possible counterexample from both directions in its own history. In 1952, a government really did conceal a disaster, sealing records and erasing casualty lists inside a closed state with no outside data access. In 2025, that same arc was covered by open global catalogs, publicly available. Able mechanism solutions and independent tsunami buoys and Pacific-wide alerts went out within minutes of the main shock. The infrastructure that hid the 1952 disaster simply doesn't exist anymore. The infrastructure that helped save lives last year is publicly auditable by anyone with an internet connection. So, what's the watch list for the coming days and weeks? It's fairly specific. The first item is the gap itself. The signal that would meaningfully change this picture is an earthquake of roughly magnitude 5.5, or larger, with a thrust-type interface mechanism located directly between this week's 2 clusters in the central Kurils. That would mean the quiet section is no longer quiet, and that stress is actively being worked through inside the gap rather than only at its edges. As of now, the center remains silent. There's a concrete number attached to that first criterion too, and it comes straight from the loading math. At roughly 75 to 80 millimeters of convergence per year, a locked section that last fully ruptured generations ago is currently carrying several meters of stored slip deficit. That energy doesn't leak away quietly. It waits, and it grows by roughly a meter every 12 to 13 years until something eventually spends it. The second item to watch is the mechanism solutions for this week's events, expected within days. Interface thrust mechanisms would strengthen the loaded segment reading. Mostly intraslab mechanisms would ease it somewhat. The third is simple persistence, whether these 2 clusters keep producing activity, migrate toward each other, or fade out entirely. Fading out is by far the most statistically likely outcome, and it would quietly close this particular chapter. It's worth saying plainly what preparedness actually looks like here now, because the contrast between 1952 and 2025 is the most genuinely hopeful part of this entire story. The same stretch of boundary that once killed thousands of people and enforced silence produced one of the 6 largest earthquakes ever recorded last year, with minimal loss of life because modern. Warnings now move faster than the water does. If this gap eventually fails, whether that's this year, this decade, or 50 years from now, the resulting tsunami will still be measured in meters, but the response time will be measured in minutes rather than nothing at all. And that difference between those two eras comes down entirely to the open monitoring network watching this arc right now, in real time, every single day. For now, the fault system has sketched an outline. 2 clusters of moderate earthquakes sit at either end of the one section of this boundary that hasn't yet failed, on an arc that has already shown twice in living memory exactly what happens when it does. The mechanism solutions should publish within days. The gap will either stay quiet or it won't. Either way, it's worth checking the map again. To put the bigger picture in perspective, it helps to step back and remember what makes the Kuril-Kamchatka arc different from most of the subduction zones people hear about in the news. This is a boundary that has produced not one, but multiple earthquakes above magnitude 8.5 within the span of living memory, on a convergence rate faster than almost anywhere else on Earth. Most subduction zones go a century or more between events of that scale. This one has managed several within roughly 7 tie years. That track record is exactly why seismologists treat this particular stretch of fault differently than most others on the planet. And it's exactly why a burst of magnitude 4 and 5 earthquakes here draws a level of scrutiny that the same magnitudes would never draw somewhere seismically quieter. It's also worth remembering that seismic gaps don't always fail on human timescales. Some sit locked for a century or more before finally letting go. Others rupture within years of the earthquake that loaded them. The Central Kuril case from 2006 and 2007 shows that the fast end of that range is entirely possible on this exact arc. The 1952 case shows what the slow accumulation and eventual release can look like when nothing intervenes for generations. Both outcomes are on the table for the section sitting quietly between this week's 2 clusters, and nothing in the current data set is capable of telling us in advance which path this particular gap is going to take. What we do know is this: a system that just experienced one of the largest earthquakes in over a century of global seismic record keeping is still actively working through the consequences of that event a full year later. The stress it shed didn't vanish. It moved, and it appears to be concentrating exactly where the geometry says it should. Whether that process resolves quietly over the coming decades or accelerates into something larger in the near term is genuinely unknown, and anyone claiming certainty in either direction isn't being straight with you. What's certain is that this is the section of the Ring of Fire that deserves the closest watching right now, and the tools in place to watch it, open data, rapid mechanism solutions, Pacific-wide tsunami warning systems, are simply better than they have ever been in this region's history. That, more than anything else in this story, is the part worth holding on to.